Assalamualaikum and Bismillahirrahmanirrahim. I am Nobati Shana Suha, magic number CD230096. We present about heat exchanger background. Heat exchanger is a device that designed to transfer heat between two or more fluid without fluid mixing. In this diagram, they have two parts, which is the blue is fluid 1 and the orange is fluid 2. Fluid 1 will flow at the tube and tube sheet while fluid 2 will flow in the shell of the tank. Next, I will present the application of heat exchanger and the associated heat exchanger problem that happen in industry. The application of heat exchanger common use is at industrial process, power plant, automotive and HVAC system. Firstly, at industrial process, they are common used to recover waste heat and preheat fluid. Next, application in power plant, they can help in condenser system and steam turbine. Furthermore, in automotive application, they use in radiator and oil cooler. And lastly, in HVAC system, they use in cooling indoor temperature. Next, the problems that common happen in heat exchanger is heat transfer coefficient, which is too high or too low level, and the falling problem. Heat transfer coefficient can leading to distort when the heat transfer coefficient is too high. But when heat transfer coefficient is too low, they can make the device inefficient, which is taking long time for heating or cooling system. For the falling problem, they can reduce heat transfer efficient with the insulation layer that can cause increased pressure drop and energy consumption that can make the shorten equipment life. This will cause high cost for maintenance. Next, I will present about the detailed process, basic part, and flow arrangement of heat exchanger. Detailed process of heat exchanger. One fluid flow through the tube and other flow through the turbine within the shell. Heat is exchanged between the two fluid through the tube wall. In first slide that I have explained, they have the blue fluid. They are they have one fluid which is blue and fluid two which is orange. The fluid one will flow in the tube while the fluid two will flow in the tank. So the process happen in the tube wall. Next, the basic part of heat exchanger. There are five basic part in the heat exchanger, which is shell, tube shell, buffers, end cappers, and heaters. The shell is the large cylinder vessel where one of the fluid flow. Next, the tube is a bundle of the small tube inside the shell where the second fluid flow. The tube sheet is the plate that hold the tube in place at both ends. Buffer is the plate inside the shell that direct the flow of the fluid and improve heat transfer. End cap and heater is the seal the end of the shell and allow fluid to enter and exit the tube. In the exchanger, they have three flow arrangement, which is counter flow, parallel flow, and cross flow. In counter flow, flow is in opposite direction, that's offering higher efficiency. Next, parallel flow. Fluid flow in the same direction. This flow arrangement less efficiency but simple to design. And the last one is cross flow, a combination of counter flow and parallel flow. This is patterned for the specific application that have a core transfer for heat exchanger. That's all from me. The next slide will show you the animation of the heat exchanger process.
Shell and tube heat exchangers will look something like this. With this design, we normally find the inlet and the outlet for one fluid at the very end of the heat exchanger, known as the header. Then we have another inlet and outlet for fluid 2 on the main body, known as the shell. Inside the unit, we have the tubes. These bend and loop around to start and finish at the tube plate, which sits between the shell and the header. The tubes will usually also pass through some baffles, which are sheets of metal. We will see how these work in just a moment. The header, as well as the tubes, can be removed for cleaning, repairs, and maintenance. Inside the header is a sheet of metal known as the divider, or the partition. This separates the tube ends, enabling the fluid to flow into and then out of the heat exchanger tubes. Fluid 1 will flow through the header, into and around the tubes, then back to the header. Fluid 2 will enter the shell and surround the outside of the tubes. The baffles will partially block the flow, which will force the fluid to turn multiple times. This creates a turbulent flow and ensures that fluid 2 mixes with itself, which ensures maximum heat transfer. For example, we might find this in a pharmaceutical factory with a boiler providing steam into the shell, which surrounds the tubes. A chemical product is then pumped through the tubes, and this absorbs the heat of the steam through the tube wall. So this product is going to exit the heat exchanger much warmer. Meanwhile, the steam will start to condense into a liquid and flow back to the boiler to pick up more heat and repeat the cycle. Additionally, these are used in refrigeration applications, like this industrial chiller. We have the water flowing through the tubes and the hot refrigerant in the shell. The water will absorb the heat of the refrigerant so that it can transport this to the cooling tower, where it will be ejected into the atmosphere. The water returns cooler to pick up more on the chiller. We have one fluid will flow through the tube and another will flow through the shell. The two fluids are separated by the tube wall and transfer thermal energy through this tube wall. The different configurations result in different temperature profiles and heat transfer. In this design, the bend at each end isn't utilized for heat transfer, and heat can be wasted here. However, manufacturing this heat exchanger is cheaper and obviously easier.
Assalamualaikum. My name is Muhammad Faris Hafizuddin bin Muhammad Zizi. My metric number is CD230298. So, I want to present about theory and method in heat exchanger on effect of volume. So, firstly, heat exchanger transfer heat between fluid menggunakan conduction, convection dan radiation. Conduction ni dia depend kepada material conductivity, wall thickness ataupun ketebalan dinding dan perbezaan suhu ataupun temperature difference. Convection adalah pergerakan fluid ataupun nak lebih difahami movement fluid. Radiation pula is thermal energy emission dan ia juga dipengaruhi oleh heat transfer efficiency. Okay, now I want to explain about fouling factor. Okay, firstly, heat exchanger performance berkurang dari semasa ke semasa to deposit fouling on permukaan heat transfer dan akan meningkatkan thermal resistance. Yang kedua, fouling ni mempunyai beberapa jenis. Contoh dia solid deposit scale, corrosion ataupun nak lebih difahami kakisan ataupun berkarat. Dan yang ketiga adalah biological fouling yang akan menyebabkan heat transfer efficiency. Okey. Fouling juga boleh dikurangkan dengan menggunakan rawatan air atau salutan bahan kimia untuk mengurangkan kakisan ataupun berkarat dan pertumbuhan alga. Dan yang keempat, when fouling is likely, lebih mahal atau lebih besar untuk heat exchanger digunakan untuk maintain dalam jangka masa yang lama dan untuk membuat pembersihan berkala. Dan yang akhir sekali, the cooling factor increase with time, temperature and lower fluid. Maksud dia kat sini, cooling ni boleh disebabkan dengan pertambahan masa, suhu dan lower fluid velocity, halaju berdalur, dan ia juga untuk and it require adjustment to heat transfer calculation. Okay, so dekat sebelah saya punya ni, saya letak formula untuk mencari unfin double pipe heat exchanger, dan dia boleh digunakan formula dia 1/UAS equal 1/UIAI equal 1/U0A0 equal R equal 1/HI plus RFI per AI plus ln D0 I DI per 2 pi KL plus RF0 per A0 plus 1 per H0 per O. Okay, now I want to explain about method for overall heat transfer coefficient. Firstly, heat exchanger transfer heat between two fluid separated by a solid wall dengan pergerakan heat through conduction and then convection again. So nak kata kat sini, dia melalui convection, lepas tu masuk ke conduction, and then dia masuk balik ke convection. Okay, so kat sini saya ada lampirkan formula untuk heat transfer coefficient lah. So air yang kecil tu bermaksud untuk inner surface of the inner tube. Yang O kecil tu maksud dia outer surface outer surface lah. So formula dia dekat sini, R wall maksud dia resistant wall equal to ln dalam kurungan D outer I D inner per 2 pi KL. K tu maksud dia dekat sini thermal conductivity of the wall material, dan L pula adalah panjang tube tu, panjang dia berapa. So kat situ saya ada tampilkan lah dia punya formula untuk mencari thermal resistance of the tube wall. Okay, this is a formula yang kedua pula. Formula yang kedua menunjukkan R iaitu resistance equal to R total equal to Ri plus R wall plus R0 or R outer equal 1 per H I inner A inner, area inner lah, plus ln diameter inner and diameter outer per 2 pi KL plus H per H outer and A outer. So maksud dia dekat sini, I tu maksud dia inner surface lah, inner surface of the wall, if the wall, and A0 ni maksud dia area of the outer surface of the wall lah, of the wall separating the fluid. So untuk the circular tube, A inner ataupun A area inner lah, equal to pi DIL, and A outer pula equal to pi D outer L, pi D outer ataupun length lah. So di mana macam saya kata tadi, DI dan DO tu bermaksud diameter dan diameter inner dan outer. Maksud dia diameter dalam dengan diameter luar lah, untuk dia punya separating wall, separating of the fluid dalam wall dia. L tu macam saya kata tadi adalah panjang wall tu lah, panjang wall tu ataupun permukaan dia lah, panjang wall tu lah macam saya kata tadi. Okay, masih. Okay, ni yang method yang ketiga pula ataupun formula yang ketiga untuk mencari effect of falling lah, ataupun overall heat transfer coefficient. So dalam heat transfer analysis ni, kesemua thermal resistance kami combine into a single resistance lah, untuk mengira rate of heat transfer between the fluid. So maksudnya kat sini, yang kami kira resistance tu kami combine untuk menjadi satu saja resistance untuk mengira rate of heat transfer between the fluid lah. So saya agak lampirkan formula dia kat situ. So formula dia Q equal to different temperature per R equal to UAS different temperature equal to UIAI different temperature equal to UOAO different temperature. So maksud dia kat sini di mana AS tu maksud dia surface area lah. A tu maksud dia A tu maksud dia area, S tu maksud dia surface. Untuk U pula adalah overall heat transfer coefficient. So kami U2 dan dia punya unit untuk U2 adalah W per M square ataupun W per M kuasa 2 lah. Dan WM02.K. So di mana dia adalah unit untuk ordinary convection coefficient H. Okey, ni adalah formula yang ketiga kami gunakan dalam problem statement yang kami gunalah dalam result and discussion dalam next lab ataupun dalam report kami lah. So, formula ni kami guna untuk apabila tube dinding tu dia nipis dan macam contoh lah, kalau dinding tube tu dia nipis kan, lepas tu dia diperbuat dari bahan yang sangat konduktif, dia punya resistance dia tu kan, dia punya resistance tube tu diabaikan dan dia punya permukaan dalam dan luar dia adalah hampir sama. So dekat sini kami cari dia punya overall heat transfer coefficient menggunakan formula yang saya lampirkan dekat sebelah tu. Dalam slide ni lah saya lampirkan dia punya formula dia dekat sini. 1 per U equal to 1 per HI plus 1 per HO. HI H inner ataupun H outer maksud dia dekat situ.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Naif bin Muhammad Zuki, metric number CD230055. I will continue for the presentation. Okay, my part is a calculation. The first problem that we choose for the heat exchanger is to calculate the overall heat transfer coefficient. Okay. If you can see, this is the problem 1. Okay, for problem 1, we must determine the overall heat transfer coefficient of this heat exchanger. Okay, for step 1, we must bring out all the information available. Okay, D1 is 2 cm and DO is 3 cm. For this, we must to convert to meter, and we get for D1 is 0.02 meter and for D0 is 0.03 meter. Okay, for rate of water flow is 0.5 kg per second. For rate of oil flow is 0.8 kg per second. For the temperature, for the water is 45 degree and for temperature oil is 18 degree. After bring out all the information, for steps 2, we must to refer the table. Okay, given two temperature. For temperature water is 45 degree and for temperature oil is 18 degree. Okay, for temperature water, we must using properties table A9 and pick at liquid because water is liquid. Okay, we must to take density, their Prandtl number, their thermal conductivity, and the last is viscosity. For viscosity, we must to density over their dynamic viscosity, and we can get the viscosity. At below, it show their pick from the table A9. Next, for temperature oil. For temperature oil, it given 18 degree. For this, we must to using properties table A13 and take out their density, their Prandtl number, their thermal conductivity, and viscosity. It below it show that we be at table A13. In this slide, it show their calculation for search overall heat transfer coefficient. Okay, before this, we must to solve average velocity, solve using Reynolds number, and the last solve using Nusselt number. We must to do water and oil. After we solve for the previous slide, we search their overall heat transfer coefficient. For this, we must to in their formula given from that we get previous slide. In this overall heat transfer coefficient, we get 74.5 W per W per M2 dot K. After that, the last is do their discussion. Okay, for the discussion, we can calculate for improve the overall heat transfer coefficient. We must use some enhanced technique on the outside, such as a fine surface. That's all from me. Thank you.
Next is a calculation for effect of falling on the overall heat transfer coefficient. For this part, the chosen example for this problem is this question. This question requires us to determine the terminal resistance of the heat exchanger per unit length, and we need to determine the overall heat transfer coefficient of outer and inner. To solve this problem, first we need to bring out all available information from question and diagram, with the assumption of the heat transfer coefficient and the Fouling factor are constant and uniform. From this question, we know that the thermal conductivity of stainless steel is 15.1 watt per meter Kelvin. Its inner diameter is 15 centimeter. Outer diameter is 1.9 centimeter. For its inner heat transfer coefficient is 800 watt per meter square, and outer heat transfer coefficient is 1200 watt per meter square. For inner fouling factor is 0.004 meter square Kelvin per watt, and the fouling factor for outer is 0.001 meter square Kelvin per watt. After we bring out all available information from question, we need to decide what formula to use. For this problem, thermal resistance equal to 1 divided by overall heat transfer coefficient times surface area equal 1 divided by inner overall heat transfer coefficient times inner area equal 1 divided by inner convective heat transfer coefficient times inner area plus Fouling factor of inner surface divided by inner area plus the natural logarithm of outer diameter divided by inner diameter all over 2 pi thermal conductivity times length plus Fouling factor of outer surface divided by outer area plus 1 divided by outer convective heat transfer coefficient times outer area. After we decide what formula to use, we need to calculate area of inner and outer tube first, and then we substitute all available information in the equation. From this formula, we will get 0.0532 Celsius per watt. To solve the second question, we need to determine total thermal resistance. Note that about 90% of the total thermal resistance in this case is due to Fouling factor. This resistance caused by a deposit on the inner and outer surface of the heat exchanger. The falling on inner surface and the falling on the outer surface contribute to this part. 5% thermal resistance is from conduction in steel tube. The steel tube separating the two fluids at resistance due to its thermal conductivity. Lastly, the remaining total thermal resistance is due to convective resistance for 76%. The convection resistance is due to the heat transfer coefficient on the inner and outer surface. Last but not least, the final step is using thermal resistance to determine overall heat transfer coefficient U of inner and outer. Using the formula U equal to 1 over RA, where U is the overall heat transfer coefficient, R is the Fouling factor, A is the area. The final answer for inner overall heat transfer coefficient is 399 watt per meter square Kelvin, and the overall heat transfer for outer is 315 watt per meter square Kelvin. To conclude, this problem is the overall heat transfer coefficient U in this question is calculated differently. One for inner surface area of the tube and the other one is for outer surface area of the tube, Ui and Uo. Due to the thickness of the tube between outer and inner, the overall heat transfer coefficient will be different. The larger the surface area, the smaller heat transfer coefficient will be. If the tube is thin, we can neglect it since the difference is slim to none. In other words, overall heat transfer coefficient between inner and outer are different unless the tube thickness is thin.
Assalamualaikum, my name is Syahrul. So right now I will present our conclusion in this project based on the title heat exchanger. In this conclusion there is two terms, which is important finding and recommendation. For the important finding, there have 6 content, and for the first one is importance and applications. Heat exchangers are essential for various industrial setups, particularly in high pressure operation like oil and gas and power generation. The shell and tube heat exchanger is highly effective in demanding conditions due to its robust performance properties. And for the second, challenges identified. There is a major obstacle impacting efficiency and lifespan, include falling, scaling, corrosion, and thermal stress. For the third one is maintenance and operational recommendation. Implement periodic maintenance protocol to address efficiency loss. Optimize operating procedures to minimize wear and enhance system longevity. And for the first, engineering innovation. Incorporate advanced materials and innovative design such as thin surface, advanced thermal material, and edge-resistant structures. Focus on design that reduce energy consumption and improve heat transfer performance. For the fifth, system reliability and monitoring. Ensure precise temperature control and continuous monitoring to maintain reliability and extend operational lifespan. And for the last one, industry advancement opportunity. Develop sustainable and efficient heat exchangers for improved thermal management systems and reduce energy costs. And for the second term, in the recommendation, there is 6 content too. For the first one is preventive maintenance. Regular maintenance is essential to address falling, scaling, and corrosion, which are common issues impacting heat transfer efficiency. Recommend measures include water treatment to reduce scaling, applying protective coatings, and performing periodic inspection for falling management. For the second one, design and enhancement. Incorporate thin surface and enhance tube geometries to improve overall heat transfer coefficient, especially during conditions with unstable fluid properties. These enhancements not only extend equipment lifespan, but also improve energy efficiency and reduce operational expense. For the third is a real-time monitoring. Implement live tracking system to monitor performance indicators such as pressure variations and temperature loss for immediate problem detection and resolution. For the fourth is material fabrication innovation. Use high conductivity materials and advanced fabrication techniques such as 3D printing to optimize modern heat exchanger design. Leverage innovative approach to improve thermal efficiency and equipment reliability. And for the fifth is thermal load handling. Account for temperature fluctuations during the design process and ensure systems are capable of robust thermal load management. And for the last one, strategic industry implementation. Employ this recommendation to achieve efficient heat management, enhance process safety, and optimize operational costs. That's all from us. Thank you.